We start by analyzing the OMP algorithm. So let's recall how this algorithm works. Each iteration starts with an inner product of the residual with all the atoms. We seek the maximal absolute value, and this points to the next atom to join the support. We compute the solution based on the support found so far and update the residual accordingly. The algorithm proceeds this way, reducing the residual energy again and again until it is small enough. In order to simplify our analysis and notations, let's assume that the true support of the unknown x is concentrated in the leading S elements of this vector. Let us further assume that the non-zeros in these locations are given in an ordered way, such that x1 is the largest in absolute value, x2 is the second largest, etc. Note that these assumptions lose nothing of the generality of the treatment that is about to follow. Let's zoom in on the very first step of the OMP and pose conditions for its success. The residual at this stage is the entire vector B. A success implies that the inner product of B with the first column of A leads to a bigger absolute value when compared to the inner product with all the other atoms that are outside of the support. Thus, if this inequality holds true, OMP's first step is successful. The approach we shall take in analyzing this condition is to replace these two expressions with simpler versions of them in the following way. We will replace the left-hand side, marked as blue, by a lower bound. Similarly, we will replace the right-hand side term, marked in red, by an upper bound. Demanding the inequality on the bounds guarantees to satisfy the original inequality. We start with the right-hand side expression, and the first thing we do is to replace the vector B by the weighted sum of the first S atoms in A. It is equal to. We are supposed to upper bound this expression, and the way to do so is by moving the absolute value into the summation. Observe that in doing so, the absolute value can operate separately on xi and on ai transpose times aj. Still in the spirit of upper bounding, we can replace the last term, ai transpose times aj, by the mutual coherence, mu, since I and j are never the same. This brings us to the final expression, which is absolute x1 times s times the coherence. As promised, this expression is far simpler compared to the expression we started with, using the maximal entry of the solution, the coherence, and the cardinality. In a similar way, we turn to treat the left-hand side expression. Observe that in the summation, when I equals 1, we get that A1 meets itself in the inner product. Thus, this term is simply 1, assuming that the atoms are normalized, and we get an inequality to x1 plus the rest of the summation. As we aim to lower bound this expression, we rely on the reverse triangle inequality and show that the above is bigger or equal to the absolute value of x1 minus an absolute over the rest of the summation. From here, we can proceed in almost the same way as before, since upper bounding the summation amounts to lower bounding the overall expression due to the minus sign. This leads to the final expression, which again uses only absolute x1, the mutual coherence, and s, the cardinality of the unknown. It is now time to use the bounds as proxies for the actual expressions. We demand that the lower bound of the left-hand side will be bigger than the upper bound of the right-hand side. This inequality is simple to manage. Reordering its terms and a little bit of algebra, we see that the dependency on x1 vanishes, and we get to the requirement that s should be smaller than 1/2 of 1 plus 1 over mu. This is quite exciting. We got that if s is small enough, then the first round of the OMP is successful. This means that the atom that will be chosen is from within the true support. By the way, is it necessarily the first atom? What do you think? Moving on, the OMP proceeds by updating the solution and the residual. The solution is based on one atom from the true support, and the residual is updated accordingly. In fact, the updated residual is a weighted average of atoms from the true support, just as the vector B was. Therefore, the very same condition on S would guarantee the success of the second OMP iterations. And again, an atom from the true support will be chosen. As the OMP commences, xk is always relying on atoms from the true support. And this implies that the residual is always of the same form, being a weighted average of atoms from the true support. Thus, the condition on S we have obtained guarantees the success of all the OMP iterations. Recall that OMP never chooses the same atom twice. This is because of the orthogonality of the residual to the already chosen atoms. This means that after exactly S steps, OMP completes its work with a perfect solution. And so we summarize the above into the following equivalence theorem. Given A and B that are defining the problem P0, if the linear system AX equals B has a sparse enough solution, OMP is guaranteed to find it exactly. The condition for this success is that S should be strictly smaller than 1/2 of 1 plus 1 over mu.